recording.
We're just recording.
Cool.
We good?
Yep.
All right, great. Hey gang, I'm Jackson. I'm sure many of you have seen me on the internet, so now you get to see me in person. So I'm here to talk a little bit about FreeCAD Robotics. This is just kind of an overview of how robotics is currently used, the pain points in robotics, and then how we could adapt FreeCAD to better suit people who are trying to do robotics applications. So, some systems and terminology. If you come from different backgrounds, you might have some of this terminology. So in aerospace, you'll see guidance, navigation, and control system, GNCS. Guidance will set your target trajectory. Navigation will tell you where you are. So navigation is not the thing that your phone will tell it is, the turn-by-turn directions and everything. It's really understanding where you are, what your position is, what your orientation is. And then control is applying control input to your actuators or whatever in order to get you back onto that target trajectory. In the robotics world, we often adapt this for other systems, not just aerospace or naval environments, where we worry more about planning, estimation, and control again. So planning is, again, setting your target trajectory. This might be a mobile robot, or it might be like a pick-and-place arm or something to that effect. Estimation of the system state, which could be your position and orientation, like the GNCS, but it could also be actuator position, the world map, so you're learning what the world is around you, trying to then put semantic understanding to it, that sort of thing, and then the control of your actuators, so your servos, motors, solenoids, and whatnot. Here's a cool little diagram out there, the map of control theory, and you'll see that planning is up there in the upper right-hand portion, state estimations directly below it, modeling and simulations right there, and then control over here. So we're going to talk in general terms about this, but I thought this was a pretty neat diagram. It describes many of the things that you want to do in this future. So in general, we're going to start off by identifying our objectives. What is it we want to do? What are going to be our requirements? How much time do we have to do this in? What's the precision, all sorts of things like that. Then we model our CAD. From there, we will generate robot description files, create a mathematical model, perform analysis on this, develop our estimator, planning, control algorithms to meet our design requirements. We'll simulate it to validate that we are meeting our design requirements, and then we'll deploy it. So, modeling in CAD. Obviously, we're here to talk about FreeCAD, but a lot of the times it's done in SolidWorks, Onshape, Fusion 360, Creo, CATIA, and the list continues on. So let's talk about a few robots that have already been designed in FreeCAD. So one of them is this robotic arm Thor. If you go to the showcase on the Discord, you'll find a lot of robotic arms. So I'm sorry I didn't point out any of those. This one has a long history. It was, I think, started in 2016 and 2017. And there's a forum on it and large community, and you can still load it up and take a look at the assembly in a modern version of FreeCAD. So another one would be the Spot Micro ESP32. There are several versions of the Spot Micro out there for doing the quadrupeds, but the ESP32 has the FreeCAD models available, so you can download that, work with the assembly, that sort of thing. And again, you can load it and work with this. This one is, I think, Assembly 2 Plus. I might be incorrect on that one. A non-mobile robot would be the Lumen pick-and-place machine for doing PNP assembly of electronics. And this is a pretty clever one. Initially, it was started in KiCad for the electronics, but a different version, a different piece of software for the CAD modeling of it. But after they decided they really wanted to commit to open source on this, they switched everything to FreeCAD. So again, you can open this one up in FreeCAD and work with it from there. And then this was one that I did for my graduate school project. So an ESP32 has 3 drone camera, mainly done in KiCad. Most of it's electronics here, but did have to model it up again in FreeCAD so I could then do different type of simulations. All right, so after we have our CAD model, we need to then import this into other environments so that we can do our analysis and simulation. So the intermediate step there is to generate these robot description files. And so what is a robot description file? Well, a robot description file is going to describe its visual components, its It's going to describe its collision components, so how it will interact with the environment around it. It's going to describe all the links and the joints that are connected together, so it's very much like an assembly. But it'll also go further and describe the masses and the inertias, and then it'll go on to talk about some other components in there. So common formats that are available are the URDF, the Universal Robot Description format, which is very common for describing individual robots. Then you have the simulation description format, which is another one that's also used for robots, but it also describes the whole world. Your scene, your environment, physical parameters, things like gravity and such. And then MuJCF is the MuJoCo format, which extends the URDF. That one is supported by MuJoCo, but it's worth noting. All right, so the components, yeah. So the links and joints, where you have masses and inertial tensors, and now with the new materials system, we can generate that directly from FreeCAD. Sensors, you augment your model with the different sensors, their placements, and their parameters. So IMUs, magnetometers, barometers, cameras, GPS, force and torque sensors. You put in your actuators, such as your servo motors or linear actuators or any other actuators you want to put on there. You add in your visual components, and you can describe this using the different file formats, the OBJ, STL, or Collada. But you could also describe it in kind of just general shapes as well. And then the collision components, and so typically you use a lesser accurate form of the visual components, so you do a convex hull optimization, import that, so you have less computation on the physics aspects of it. All right, so what does a URDF file look like? Well, it's an XML file, and these tend to be very long, so hundreds to thousands of lines. And there are a couple of ways to generate things. One is by hand, and the other is using a tool, like out of your CAD software with a Workbench or a plugin. Well, most of them are written by hand. So you could write it in XML directly. That's not as common. A lot more common is the Xacro macro language, which uses macros so you can support properties and property blocks. You can set all your parameters. You can set in math expressions, conditional blocks. You have your defaults in there, so you don't have to constantly describe your parameters. You can dynamically rename your elements and attributes. So if you have an array of something, you can use that, and then you can do loop unrolling. If you go online, you can find publicly available description of these robots. Most of them are robotic arms. Most of it comes from the Ross Industrial project, where they describe various robot arms which are used in industry. There's a bunch of other sources out there. So Xacro dominates the URDF generation. It is 95% of what's available publicly, at least. And unfortunately, there are a lot of errors out there. So this is a list of errors that came from a publication where they just did a broad analysis on publicly available robot description files. And you can see here on F, these are invalid XML files. So it's actually, some of them are just not even valid files. It ends up out there. So here's an example, the Allegro hand. So if you start off with this, you can go, this is a commercially available hand that you can purchase, and they'll provide a STL form, the CAD model. But you can go online and get the dimensions and the directions of each of the joints. You can get the links masses, and then you have the limits of motion that is available for each of these. And from there, you can then construct your Xacro file. So this is just a portion of the Xacro file, which shows that they're using properties and they're naming them and associating them with values that come from that table. And then the output will then end up being that XML file that I showed earlier. But that's really painful, especially if you have to go through and iterate on this design. So you make a change in your design, you have to make sure you go back and correct everything else. Otherwise, you've now got inconsistencies in your system, and what you may end up releasing or simulating or testing may not match what you've actually produced as a physical item. So, what about CAD assisted? Well, the Ross group released a SolidWorks URDF exporter, but it was last updated for SolidWorks 2021. There is a few open source ones out there, so Fusion to URDF, so for Fusion 360. There's a recently developed one called Export URDF, which is trying to support multiple different CAD systems. So they currently support Fusion 360 and Onshape. There's a PTC Creo to URDF. And there are a few FreeCAD workbenches. The Robot Descriptor is an earlier project that I think started in 2016, and then it became, well, it was as Robot Creator, now it's Robot Descriptor, but it gets developed and starts and stops. And so recently there's been Cross and Overcross, which are open source, and then Southwest Research Institute created Sword, which is a commercially available option as of earlier this year. Okay, after you've got your robot model, you import it into your favorite robotics framework, and from there you can create your math model by hand or a tool-assisted approach for your analysis. And then what you want to now analyze is oftentimes observability and controllability to ensure that you can observe the things you're interested in observing. So whatever states are important to your system, and then control those states. And so there are a few options. ROS. You can import into a variety of components. So ROS isn't a single component. You can import into a variety of components. Drake from MIT and Toyota Research Institute is another one. GT Dynamics from Georgia Tech is an approach. And then in closed source, NVIDIA's Omniverse, notably their Isaac Sim system, the MATLAB Robotics System Toolbox, and the MathWorks SimScape Multi-Body System also import these and allow you to perform analysis. All right, so once you've got it in there and you've confirmed that you can measure you've confirmed observability and controllability of your system. Now we want to go ahead and develop our planning, estimation and control system. So for planning, you might use an ARM motion planning system, or maybe a mobile robot motion planning system. Estimator, you might employ some sort of SLAM algorithm, or if you have multiple robots trying to share information, you might employ a decentralized data fusion system where they can now share information. For controls, you might end up applying a model predictive controller or linear quadratic regulator, H infinity, or on and on and on, to do whatever it is you need to do. After that, you want to confirm that it's going to solve your problem. So you need to import this into a simulator. Gazebo is probably the most common and well-supported simulator. There are a few others that are worth noting. PyBullet, which has a long history of open source development. PyBullet Industrial, which is now targeting those robotic arms. Tiny Differentiable Simulator, which came out of Google Research. MuJoCo, which was a commercial offering until a couple of years ago when it was acquired by Google DeepMind and made open source. Hollow Ocean from BYU is targeted towards ocean simulators. So you can find a whole host of simulators that are targeting either general environments or specific environments such as the Hollow Ocean. And in closed source, there's a lot of options available too. So the Isaac ROS system, so you have Isaac Sim for ROS, MathWorks multi-body, and the system, the robotic system toolbox there. So Gazebo is really well supported. There's a whole host of different approaches, environments in which you can simulate and operate your robot. And it is the de facto go-to for most systems. If you're working with PX4, whatever, they have a lot of guides for that. PyBullet was originally bullet physics by Erwin Koemans, and he's been working more and more in research. And so here's a recent publication that employed the PyBullet system. And they used it for robotics training of neural nets. It's been featured in many video games and simulation systems in the past. And the most recent release was in 2022. Since then, Erwin got picked up at Google to work on this tiny differentiable simulator. It's a header-only C++ library for doing simulations. It was designed for reinforcement learning, so there's a neural net component in there that you can train along with performing your simulations. And they're able to simulate on a desktop RTX 2080 NVIDIA graphics adapter thousands of these Unitree Lycago robot quadrupeds at a rate of 50 frames per second. All right, MuJoCo. This one was originally a closed source product that was recently open sourced in 2022. It was featured very heavily in the OpenAI gym, so if you competed in any of the OpenAI gyms, this was the physics engine that they were using behind the scenes. This one's pretty elaborate. It supports soft robotics, tendon and cable-driven systems, just a whole host of platforms that a lot of simulators don't. And then Drake from the MIT Robotics Locomotion Group and Robotics Division at Toyota Research Institute. This one is also very comprehensive. They're focused primarily in industrial robots for Toyota's research. All right, once you've simulated and you've validated that your robot's going to meet your objective, now you need to deploy it. If you already wrote it in C or C++ and or Python, you're using ROS or Drake, GTSAM, SimForce, or one of those other tools, you probably just compile it and deploy it on your machine. If you're using one of these other tools that uses MATLAB or Simulink, you'll need to do code generation to target your platform. And then once you do your targeting your platform, you usually connect that up back to your simulator and do a hardware in the loop simulation to ensure that it will run on your platform correctly. So what are the pain points? Well, we've already seen one, the URDF generation. Manually writing these URDF files is a real error-prone and time-consuming process. And it's not linked to the underlying CAD model. So if we change that CAD model, we have to then modify our URDF files. And if those fall out of sync, we may end up with some surprises that we don't want. The assembly. So assembly workbenches really don't include actuators or sensors. So they're not, when you assemble your robot, you then have to use something else to add these different components in there. And they may not have features such as the range limits, or they may not compute the masses or inertial tensors that you'd want in the URDF files. And then the time to validation. So going from one tool to the next tool to the next tool is a time-consuming process that may slow down your progress. So if we could integrate that into the CAD system, that would be a huge benefit to reduce that pain point. So there are a couple of existing FreeCAD workbenches. The Robot Descriptor, it's a work-in-progress workbench, and it's intended to work with the SDF files. It's off and on since 2016, but recently Cross and its fork Overcross have been under heavy development. Gail Eckhard, his ROS workbench for FreeCAD, it is itself an assembly system. So it has its own assembly system, its own way of doing things. It's not compatible with other assembly systems, but you can export to assembly 4 from it. This one actually supports importing and exporting of the Zacro files as well as the URDF, so you can import existing robots. But this is, I think, its neatest feature is the interoperability with ROS. So within FreeCAD, it will connect out to different components via ROS, so you can have an external simulator, which will then provide feedback to FreeCAD so you can see how it moves and animates. It also has the ability to display motion planning for ROS Move It. So if you are doing a pick and place or some other machine with a robotic arm, you can visualize that trajectory, that's built in there. But I think we could address this. Right now that's a workbench I just recently discovered, so a lot of these are probably covered by that, but extending the assembly workbench would be a great way to make this more easily accessible to those who want to do robotics work by permitting importing and exporting of the URDF files and adding actuators and sensors to the assembly workbench, interacting with tooling to do analysis, simulation, and deployment, and then creating a library of common sensors and actuators. So examples would be if you want to add a camera, you can use the Intel RealSense D435i or one of these MEMSense IMUs on there, or a standard RPI LiDAR. So there are these standard components that don't have to be custom electronics that we could put in there and have available to build and test out a library. So yeah, that's my presentation. Thank you. Yes?
If we were to add something to assembly, are these properties have to be supported by assembly, or simply that we can add the properties to assembly? Like, can you declare a particular object to be a actuator?
Mm-hmm.
Is that all that would be required, or does it have to be a very specific, is there more to it than that than simply a declaration? Or like a range, even if the assembler doesn't honor the range,
Mm-hmm.
but we allow you to put the range in, would that be enough, or is there
to generate the URDF or SDF or the other robot description file? Yeah, that would be sufficient. Absolutely. The ability to generate that file and be able to update that file from within that CAD is exactly one of those big.
So it's largely adding more data. It's not necessarily adding operations to the assembly.
Yeah. One of the areas in which I am interested in is the ability to switch out perhaps the solver component and then be able to import a different solver. One of the solvers that was listed, like tiny differential simulator, would be a pretty neat approach, and see how that would interact there. A full simulation environment might not be ideal, because that really kind of expands way beyond what a CAD system would typically do.
That'd probably be best as a separate workbench, I suspect.
Yeah. But as far as how can we generate a robot, could we add those properties in there and be able to identify your sensors and your sensor parameters, your actuators and actuator parameters, generate those inertial tensors, that sort of thing. That would be huge.
Have you seen the work that Peter Hema has proposed? We've got an FPA grant where he's talking about adding, it's a property system, right? It's a generalized property system that we're going to fund for the FPA over the next 3 or 4 months.
Awesome.
So the ability to add completely arbitrary properties is coming. Not for 1.0, but I mean, it's 6 months from now you're going to have that.
So you're just saying create completely custom properties.
Yes, essentially,
Assign
just
them
arbitrary, I mean, because all this stuff is, I mean, it's Python objects, right? It's,
Right.
you know, assign whatever data you want to it. So we're gonna have a system that is documented and available for doing exactly that. That's Peter Hema, Hiejma, I think is how that's spelled. So if you check out the FBA, the grant proposal repository, you'll see that it's the most recent one we funded.
He recently did the VARSAT stuff, is that correct?
Yes, yeah,
All right.
same guy.
Awesome.
All right, well, thank you.
Thank you.